संदीप जी आप शुरू कर सकते हैं.
Okay, so we'll start now. So yeah, welcome to this seminar, and it is my great pleasure to introduce today's speaker, Professor Sudhanshu Shekhar, who is a faculty member in Department of Mathematics and Statistics at IIT Kanpur. Before joining IIT Kanpur, Sudhanshu was a postdoc in Heidelberg, and before that, he did his PhD under guidance of Professor Sujata at Tata Institute in Mumbai. And today, Sudhanshu will speak on Galois representations and modular forms. Sudhanshu, hi, to you.
Okay, so thank you, Sandip, for the introduction. Thank you for the invitation. This session is for describing Galois representations associated to Hecke eigenforms. So plan is that I'll begin by some generalities, some statements I will make from this subject, and then after that I'll state the main theorem, which will describe a Galois representation associated to a Hecke eigenform, and then state some properties of those representations. And after that, briefly I'll discuss its construction. So while I discuss construction, there will not. So, while doing that, I will define some of the objects which appear there, and then how they appear also I'll explain. However, there will not be any detailed proof. For detailed proof, one really need to look at the original article of Galin itself. But basically what I will do is that I'll break the main statement and main theorem, basically the construction of Galois representation in several smaller statements, and I hope that that will give an idea how it works. So let us begin. So an important problem in number theory, particularly algebraic number theory, is understanding this group GQ, which is the absolute Galois group of the field of rational numbers Q. And to understand a group, what one does is that basically try to understand its representations. So understanding GQ is essentially same as understanding all its representations. So here I have written representation rho of GQ in GLN of C, but you can also take other fields here like CP or finite algebraic closure of finite field, or other fields also, or in fact rings also. So that's looking at these representations, one gets an idea of the group GQ itself. The special case of n equal to Q is dealt using class field theory. In particular, recall Kronecker-Weber theorem, a very important classical theorem, which essentially describes finite extensions of finite abelian extensions of Q. So, or in other words, characters of GQ. So every such character factors through a cyclotomic extension of Q. This is what this diagram describes. And if I replace here, these are continuous representations, that is why they will factor through a finite extension of Q. But if I replace C star by other field, let's say here QL star, and then continue to assume that the representations are continuous, and then we get more representations. One such important representation is the cyclotomic elliptic cyclotomic representation of GQ. This is how it is defined. So here we take this extension of Q by joining all L power roots of unity of L power root of unity, and then we get the surjection of GQ to this Galois group, which is actually isomorphic to ZL star. Isomorphic to ZL star. L is a prime number here, and so this is how cyclotomic character, elliptic cyclotomic character is defined. And here is a correspondence. It says that representations called geometric elliptic representations. I'll say a little bit about it. I'll not give you complete detail, but say a few words about it. So what are geometric representations? So geometric elliptic in particular, the characters of GQ corresponds to what we call the Dirichlet character, that is finite order characters, and this elliptic cyclotomic character. So these are all geometric characters of GQ. What is a geometric representation in general? So it's representations which are unramified outside a finite set of prime of Q, and also it need to be what we call potentially semistable representations. So I have written here actually semistable representation at L. In fact, the definition actually, if you look at anywhere, it says that semistable, potentially semistable everywhere. But actually, one knows that if I take a representation of GP, so GP here is a decomposition group at a prime P away from L, then elliptic representations of this group GP at primes away from L are actually always potentially semistable and statically authentic. So it's either unified. Yes.
What is semistable?
Yeah, so that's right. So I'll not define it I mean great detail, but of course at P if you want to define semistable at P, it requires one of those rings of defined by Fontaine. But away from P, we will be looking mostly here two-dimensional representation. So you can take it representations of this kind.
And right, unramified means representation is semi-simple or something more.
Yeah, it just means that the restriction to inertia group is trivial. So it's just a representation of, I mean, Z hack. Okay, so that's what it means. Definition of unramified just is that.
Yeah, the unramified. So it's a representation on Z mod P to the N, something like that, right?
Yes. So okay, let me just describe what is unramified.
N star. And
yes, I have. Okay, I'll describe what is an unramified representation. Let me
yeah.
just quickly say, do it. See, I have a representation of. Sorry, it's moving. So, okay, so I have a representation of GQ. I'm very sorry, it's something. There is some problem with the screen itself. Okay, so I have a representation of GQ.
Yeah.
And so inside that I have for any, if I take a prime, let's say a prime P, then at this prime I have a group. Inside that I have a group what is called inertia subgroup at that prime PP. So if I take a representation which is trivial on IP, then I say it's unramified. Okay, if it is non-trivial on IP, then we say it's ramified. That's the definition. Okay, so a representation is a function from GQ to GLN of I mean whatever ring or field you take. So I can restrict that representation, that function to an inertia subgroup. IQ is a subgroup. I can restrict it there, and I can ask whether its image is trivial. Trivial means identity or not inside GLN of that ring R. So if it is trivial,
so what does it mean in terms of number theory, so to speak?
Number theory. So of course, if you want, let us look at this
inertia is a standard objects. I know.
Yeah. So let us look at, for example, here. So here, if you look at this Q of zeta n over Q, so these extensions here in this extension, inertia subgroups are non-trivial only at. I mean, inertia subgroups are non-trivial away from primes dividing capital N. Okay, so yeah, so at those, I mean, so at those, so elements in, so if I have L which is not, if I have a P not dividing N, then it's unramified there. Of course, so when we look at the, for example, modular forms, they will be semi-simple. That thing is there, but that's not just coming from definition. Definition just says that it's unramified. Okay.
Is it equivalent to?
No, it depends on the coefficient. So over C, it will be like, for example, it will be semi-simple. But if you, for example, look at finite field, so you can have a representation of this kind. So you have a, let's take a degree P extension of GQ, and then a two-dimensional representation. You can take its image, which is landing inside. I mean, its images of the matrices of the kind one on the diagonal and non-trivial on the upper corner. So then it's not going to be semi-simple. So it depends on what coefficient you are taking. But over C, it will be semi-simple. I mean, characteristic 0 also you can take, but whenever you have other rings, then it's not going to be. It need not be. Okay.
Okay.
So it depends from where the representation is coming, and it's a property of representation, not just the fact that it's ramified or unramified.
Okay.
Okay. So another example, it's not like equivalent. So for example, you can have, let's say, what are called tachymolar characters. So tachymolar character, it's like if you take characteristic 0 field, or if you take a even characteristic P field, then because the order of the character is prime to P, it's semi-simple. Representation is semi-simple, but at P it's not unramified, it's ramified. So both the things are not equivalent.
Okay.
It's being semi-simple, it's something else, and being unramified, it's something else. I hope it's clear. Yeah, but for modular forms, when we look at modular forms, then we'll see. Okay, I will not discuss that here, but you can see that away from P, they are all actually semi-simple. Sorry, away from the level of modular form, they are all semi-simple.
There are some questions in here.
Sudhanshu, I think you can go ahead. We can take the questions at the end. No?
Yeah, okay.
Please, yeah.
Just a minute. I have to close this chat. Okay, yeah. Sorry, this screen was a little bit, I don't know why that was happening, but yeah, so yeah, so I was here. As I said, so in the case, okay, someone was asking what is the meaning of semistable. So I can just say this much, that if you take a prime, for example, in the modular form case, it essentially means the image of this Galois representation at primes away from P. It will be of this kind. It will be taking value 1, 1. And some star here and star here. Okay, so yeah, so restriction to inertia. So for example, if it is unramified, then star will also be 0. Okay, so that's what it will mean. I'm not defining I mean, particularly at the prime P, because it requires techniques from Haas theory, but we don't need it. So let us I was just trying to make this statement because somehow this context is important. Okay, so what about all these things were n equal to 1? So what about n equal to 2? So again, there is a correspondence here. And here, so elliptic representations, we are interested in representations associated to modular forms, actually Hecke eigenforms. So in this case, elliptic representations associated to modular forms of weight at least 2, and they correspond to what are called odd representations. Odd elliptic representations of GQ of degree 2 of what are called, as I said, it's when you look at the representations at P, it's these things, what are called Hodge-Tate weights comes. Again, this we will not need when I state my main theorem and describe its construction of the representation. But let me just make the statement that they correspond to representations of what are called of degree 2 of distinct Hodge-Tate weights. These are all so this happens up to cyclotomic twists. Okay, so here if I look at this correspondence, the one direction, this containment is due to Eckler, Sumura, and Dalin. So Eckler and Sumura actually they did it for weight 2. In that case, the representations are actually coming from abelian varieties, and for higher weight, it's due to Dalin. And the converse direction, it's actually part of the proof of modularity conjecture. in that case, it's due to the several people, starting with Wiles and then Wiles and Taylor Wiles, and then Berger and others. So so we are interested in this side inclusion, the construction of Dalin, construction of Galois representation by Dalin, and that's what we're going to describe in this talk, in this lecture. So let me fix some notations. So let us take an integer n and another integer k, k to be a positive integer. We will be mostly looking at k greater than or equal to 2. Maybe I'll just make one particular statement for k equal to 1. Otherwise, we'll only looking at k equal to 2, k greater than or equal to 2. And let us take a character epsilon z mod of z mod nz star to c star with the Dirichlet character. And then consider this group gamma n, which is defined as the kernel of this SL2Z to SL2Z mod nz, and let me just recall the definition of what are called congruent subgroups. So a congruent subgroup is a subgroup of SLNZ which contains gamma n for some n. And these are two examples of congruent subgroups we are interested in. I will mostly be talking about this gamma 1 n, but there will be few statements about gamma naught n. So what is gamma 1 n? These are those matrices in SL2Z which satisfy this property that A is congruent to 1 mod n and C is congruent to 0 mod n. Okay, and gamma naught n are those things which just satisfy C congruent to 0 mod n. Okay, so gamma 1 n is a sub of gamma naught n. So these are the two such subgroups. Now, for a subring R of C, or in fact, even one can take CP, but I will mostly taking subrings of C. We denote by Mn of gamma 1 n semicolon R. So let this be the set of all modular forms of weight K with coefficients in R. So by coefficients what I mean that their Fourier coefficients are in R. So I take those modular forms with Fourier coefficients in R and its level n. This is denoted by Mn gamma 1 n comma R. This is actually an R module. If R is a field, then it's a vector space. And in particular, if I take these kind of rings which contains all the image of this character epsilon. So remember, we had this character epsilon which I had fixed. I have fixed here right in the beginning. So if I take a ring which contains the image of this character, so basically there will be roots of unities. Then we can define also the smaller space, what are called modular forms with Niven types. So these mk gamma naught n epsilon R denote the set of all modular forms of weight k, level n, and Niven type epsilon with coefficients in R. So I'm not really recalling the definition of modular forms because I believe it's a series of lectures and there are several lectures already where I think these things have been discussed in details. Though I will describe these groups in a slightly different way than usually it is done for my purpose. So in these mk gamma naught n and mk gamma 1 n, inside these there are certain further subspaces or submodules called the space of cusp forms. So they are those forms with zeroth Fourier coefficient to be 0, and so I denote by sk gamma 1 n R and sk gamma naught n epsilon R by the space of cusp forms. And we also have the notion of Hecke algebra. So you can take so once we have these spaces, these are we can take the endomorphism ring of these modules over R, and inside that we can take the subalgebra generated by Hecke operators Tn's. Again, I'm not recalling those definitions of those Hecke operators, but
Your definition.
Yeah. So and we can take the algebra subalgebra generated by Tns, and that we denote by Hk gamma n, actually it should be gamma 1n and gamma again it should be gamma 1n and Hk gamma 1 and r, and then if there are if I'm looking in space with Niven types, then I will have epsilon here, otherwise no no Niven type. So corresponding to, so it depends on the space itself. Okay. Now let f be a. So now let us. So I defined all these things with any ring R. In fact, you can take ring R to be any z. So any z z1 by n algebra. Even if, like, say, finite field whose characteristic doesn't divide n, all these things will work. But let's now, for now, let us just focus with rings which are inside C or CP. So let F be a primitive form with an even type epsilon. So these are primitive forms which they are the eigenforms or all Hecke operators Tn's, and also not coming from some smaller level. So they are primitive forms. They are called primitive forms. And let capital K be. So maybe I'm sorry for this notation of capital K, and the weight also are denoting by K. This may be, I hope that doesn't create confusion. I think it will be clear from the context. So let capital K be the number field and defined by field obtained by adjoining Fourier coefficients of that eigenform F. So this is a number field that requires proof, but it's a consequence of the fact that Hecke algebra itself, for example, Hecke algebra with coefficients in Z is a finitely generated Z module. So from there, actually, there is some integral relationship between elements of Hecke algebra itself, and that actually from that one gets that these ANs are all they all lie inside a number field for a fixed F. So now I have this number field KF. This depends on F, and then what I can do is that so given I fix a prime L, and then in KF there could be several primes of KF lying above this prime L. So for every prime I get a completion of KF at that prime. Of course, that means you'll have, if there are finitely many primes, you get finitely many such completions. But I'll use a kind of, say, Bishop notation because that will not create any confusion here. So for all such primes, I'll use the same notation. I'll not use something else. I'll denote it by KL itself. Okay, so KL is the completion of KF at a prime of KF dividing L. Okay, so now, as I said, there are several such completions, and we will be so Galois representation associated to F will have coefficient in this KFL. So in fact, strictly speaking, you have not so as many primes are there in KF lying above L, that many representations you get. Okay, for every such prime actually you get one. But we choose one, and we'll just give a construction to one such prime. We describe one such representations for one such prime. Okay, so now so again, so since F is an Hecke eigenform, and there is a KF algebra homomorphism, we denote it by lambda F, or sometimes I'll just denote it by lambda if F is understood from the context. So there is a homomorphism here, which takes Tn to An of F. Okay, so so the main theorem of this talk is that there is an absolutely irreducible Galois representation rho F comma L from GQ to GL2 of KF comma L, such that, so here are the properties of these representations, which actually describe the representation also. What are those? So first one is that the term which appeared in the beginning of the talk, that rho FL is unramified outside NL. So one of the properties of this being geometric is satisfied here. Yeah. So it's unramified outside NL. It's prime dividing capital N and L. And for each prime P not dividing NL, you can also say what are the traces and discriminant of this image of traces of discriminant of the image of Frobenius at the primes. So you have given you have a Galois representation here. You have absolute Galois group GQ here, and inside that at every prime, you have this decomposition subgroup, and then here you have a class of Frobenius element, which I'll be denoting from here, and then on that, if you look at look at the all these. So this representation rho FL is unramified outside NL, that we know. So we can, so it's trivial on the inertia. So that means we can evaluate it on Frobenius element. It's well defined, value is well defined, and we can talk about what is that matrix. So the determinant and trace of the matrix is can be described using this polynomial. So that image of Frobenius basically satisfy this. Okay, so in fact, this is nothing but, so this quantity is actually equal to the Fourier coefficient AP of F. Okay, this should be cyclotomic actually. Yeah, sorry, this should be epsilon actually. Sorry, there is error here. It's an even type. So epsilon is an even type of F. Now its determinant. If I look at the determinant of this representation rho FL and evaluate it at a complex conjugation, and so it's embedding of Q bar inside C, and from there we get a complex conjugation on Q bar. And if I evaluate this determinant of rho FL at that element of the Galois group, its value is -1. It's order 2 element. C is order 2 element, so it's an order 2 element. So its value will be either +1 or -1. And if it is a Galois, rho FL is a Galois representation associated to a Hecke eigenform, then Hecke eigen actually cusp form, then its value is -1. This is what, so there was a term some time back that these representations are odd representations. This is what it means if I say, it means a representation being an odd representations. This is the definition. Now, this is about the value at complex conjugation, but in general, also you have the determinant character is nothing but the product of even type and power of cyclotomic character. So this power is what tells you what is the weight of modular form. Okay, so it's, if I have a weight K modular form, then it's K -1. This is where one gets the weight of modular form, and yeah, sometime I had used chi cyclotomic, sometime chi L. So this is the elliptic cyclotomic. Sorry for this confusing notation. This is the elliptic cyclotomic character of GQ. Okay, so now, so these are the, maybe I'll just again make this slide smaller so that you can see all the properties at a time. So this is the most, the main theorem of the talk. So maybe I guess it's better to have a look at it and at all the properties of, and these are additional things which I had written. So I'll just remove it so that there is no confusion. Okay. Yeah. So this is the statement, main statement of the main theorem. It describes the representation and some properties of representation. And yeah, so let me make some remarks. So as I said, you have what is the, how, the polynomial which is satisfied by, so you know how the Frobenius act, you have some knowledge about the action of Frobenius on these representations away from the prime dividing NL. So from there, actually, what you can also describe what is the determinant and trace using that, because using that degree 2 polynomial determinant of it also you can describe it using this property or using that matrix. So you can describe that. You can say that determinant of image of Frobenius is epsilon evaluated at P and P to the power K minus 1. And trace is equal to APF. Okay. And this is a consequence of this can be proved using what is called Euler-Semura congruence relation, which I believe was there in, I think, one of the lecture in the previous week, last week, and so yeah, so it's the Euler-Semura congruence relation actually tells you how this Frobenius acts on this vector space VF corresponding to this representation. Now, other thing is uniqueness. So, because I said, you remember here, I have already said this is an irreducible representation, absolutely irreducible. In fact, basically it means that see, it has a coefficient, representation has a coefficient in KFL. So you can go right up to algebraic closure of KFL. It remains irreducible even there. That's what it means. Being absolutely irreducible. So the absolute irreducibility plus this property, its value on, because you know its value of the traces and determinant away from NL, or I should say all but finitely, at all but finitely many primes. Using these two properties, you can, in fact, one can easily show that it's so it's there cannot be any other representation with these properties which I have described just above this in the main theorem. So Chebyshev density theorem one need to use, and plus this irreducibility. So using these two things, you can say that if you have any other representation satisfy these properties stated in this theorem, then it got to be the one which it got to be the one which I am going to describe now. Okay, and as I said, k equal to 2, it's due to Euler and Semura. It was done long back in 1950s, and for higher weights, it's by Dalin. And I have said that I will be mostly considering only weight greater than equal to 2, but at weight 1 also one has actually one can construct a representation associated to eigenforms. Although construction is a bit different there, it requires a different kind of methods. However, there is a construction. It's due to Dalin and say. Now, so these were mostly the global property in the sense that how the representation looks like on, except these maybe. These are the global property of representation. That is how it looks like. What are its property on GQ? But what about local property? So its restriction to decomposition subgroups or inertia subgroup. That is something also one would like to know. So here are certain properties of these representations. So FL at primes, particularly, so this property is at the prime L itself. So this case is what are called ordinary representations. So in that case, it's upper triangular. So if I have, so see, you have representations. So it's a representation of GQ. Let me just write down here. It's a representation of GQ. So for every prime P, you have decomposition subgroup inside this. So there are two cases: P equal to L and P not equal to L. So at in these two different cases, representations behave differently. So when P equal to L, so when P is equal to L, this is how it looks like at the decomposition subgroup. So it's upper triangular, and this quotient delta is actually unramified. So its restriction to inertia at the prime dl. So at restrictions inside this you have IL. So its restriction to IL is trivial of delta. However, chi, that is not the case. In fact, here is what here this can be described in terms of cyclotomic character and the event type. And however, one one also knows, not just one knows not only it's unramified, but what is its value. Or once I have this representation unramified at a prime, so it's on GP, and then I have inertia IP. So it's trivial on IP, so it's a representation of GP mod IP, which is generated by Frobenius. So I can evaluate it on Frobenius and ask what is its value. And so value of delta at Frobenius at L is given in terms of TL. So image of, so remember we had a homomorphism lambda from the Hecke algebra to KFL. So that so we can look at the image of these Hecke operators TL and UL via this homomorphism, and it's there are two different cases whether L divide N or L doesn't divide N. If L divide N, and then it is the image of UL. If L doesn't divide L, then it's L doesn't divide N, then it's the image of TL. So these are the two different cases. Okay. Yeah. So this is the precise. Value of this is how you can describe delta Frobenius at L. So here I should say that this epsilon L, so if L divide, so remember epsilon was a character of Z mod N Z star. So if L divide N, then we take this to be 0. Okay. And so this is at the prime. So as I said, there are two cases, P equal to L and P not equal to L. And we want to describe the property of this representation, its restriction to DL when L equal to P and L not equal to. So L equal to P, this is the case, and L not equal to P, here is the description. This is due to Langland and Carayol. It requires one needs local Lagrange correspondence for this statement and coming from there. However, let me say that. So I have already in the beginning of maybe in first or second slide, I said that representations away from P are already potentially semi-stable. So so when P is not equal to L, then it has this certain special forms. There are two cases. In one case it is of this form, and in another case it is of, I'll come back again in this form. But if I restrict it to inertia, then yeah, these two will be trivial one, and here it's non-trivial, and here also same. These are all unramified. So it's already, we see that I have in the beginning I said that away from P it's potentially away from P semi-stable means it's upper triangular and diagonal entries are one. It's that this form. So we already see potentially it's always this form is there from it is coming from the result of Grothendieck. However, potentially means going to some extension. However, without going to that extension, if you want to describe it describe its values on the decomposition subgroup GP for over Q, then in that case it's some more. One need to look at more carefully, and it's due to Langland and Carayol that in two different cases, representations are of this form. So let me just describe those two cases. So when P is not equal to L, is prime. Let's see with the conductor of epsilon, and so you remember epsilon was the character of Z mod and Z star, but it may factor through even a smaller group. So you choose the smallest C such that it factors through Z mod C Z star, and that is the conductor of epsilon. And similarly, one can actually define the conductor of modular form also. However, that is described in terms of level of the form. So when so we have if it is F is a new form, then conductor is n itself. So let's assume F is a new form, then we can write down C in this form, p to the power E prime C prime, where C prime is co-prime to P, and we write n also in this form, and again n prime is co-prime to P. So if E and E prime are equal, then restriction to inertia, if you look at, then it's upward triangular. Sorry, then it's semi-simple. So it's of this form. It's direct sum of two characters, trivial character and the Nivente. And this is the description on inertia. And if I look at the description on decomposition subgroup, then again it's semi-simple. It's direct sum of these two characters. This one is unramified. This one is ramified. For unramified character, here the description is there. It's image again. Whenever you have a character or representation which is unramified, it becomes a representation of GP mod IP. So that is generated by Frobenius. I can evaluate it on Frobenius. So this is how it is described. When E equal to 1 and E prime is 0, then again there is a description. In this case, it is not semi-simple, so it can be non-trivial. However, these two characters are unramified, and yeah. So again, you have description of this unramified character in terms of description of this unramified character in terms of UP. Yeah. So these are the properties. These are in two cases I have described this property of this representation, and there are several more cases remaining. So these are not the only cases. There are certain cases. See, both these cases, you see that it's diagonal. These entries are 0. So that means representations are reducible. But it can be, in some cases, it can be reducible also. So those are what are called supercustodial representations actually. But yeah, anyway. So there are some other cases remaining. But these are the two most important cases, basically semi-stable cases. Here is a convert. So this is about given a modular form, you have a representations. And given a representation, when can you get a modular form such that the representation is coming from modular form? So the converse statement is also there. It's converse of that. Remember, there are correspondence in the beginning of talk I had described. So one direction is what, so I have described whatever I have described so far is one direction. The other direction, the converse direction, here is a special case of that. The special case is again the ordinary case. So we say that if I have a two-dimensional odd compatible system of representation, so let's not bother about this. It basically means that we have a representation at every prime L, which is compatible in some way. And with the same property that determinants take this form, and at restriction to decomposition subgroup at so this should be L, I guess. This should be L. So for some prime, so again this should be L. So it's of this form. Then it comes from a primitive form F. The representation is actually rho F is rho. This rho L is equal to rho FL for some F, and all those. These coefficients are related to the Fourier coefficients of F. So this theorem is due to Hecke and Winton-Berger. It's a converse statement. Let's stop the converse case here itself and again come back to our case. And that is the representation rho FL itself. This is what we wanted to discuss. So how this rho FL is constructed? That's the question, and that's where geometry comes. So as I said, we have already seen that it satisfies the properties of for representation to be geometric. So it should come from geometry. So we need to discuss geometric interpretations of all these definitions of modular form, and that's what we are going to do now. Okay. So now let me just, so before I start describing its construction, let me state basically conjecture. You can view it as a motivation basically for this representation to occur. So here, so a continuous irreducible representation of a continuous irreducible QP representation of GL. L is a number field. You can take Q equal to L equal to Q. In that case, representation of GQ. So then a number field L is said to come from algebraic geometry. So earlier we had a geometric representation, now we have a notion of representation coming from algebraic geometry. So we say it comes from algebraic geometry if it is isomorphic to a subquotient of an étale cohomology group of with étale cohomology group of a variety with coefficients in QP R. So this is an art twist of, it's like art power of cyclotomic character. Okay, so for some, yeah, that's what by that I mean when I say tail twist, that's what I mean when I say tail twist. So it's like art power of cyclotomic character. So if it is a subquotient of HI et al, HIX et al with coefficients in QPR, then one says that it's a geometric, it's a representation coming from geometry. And here is a well-known conjecture in the subject. We say that an irreducible periodic representation is geometric if and only if it is coming from geometry. If
algebraic variety over L, right? Not of L. What is of L? It is algebraic variety over L, right? Last
yes, over L. Yes, algebraic variety over L. Yeah, that's I have written it here. So if we are interested in over Q, so it should come from a variety over Q. Our representation of modular form. Okay, so the conjecture says that it is geometric if and only if it comes from algebraic geometry. Okay, so this tells you that if you want to construct row FL, we need to have a variety. We need to construct a variety and look at. We need to have a variety and have some kind of sieve on that and elliptic sieve, and then try to construct this representation.
Excuse me, can you please recall what did you mean by geometric representation? I mean the first one.
Yeah. It's unramified outside a finite set of prime and potentially semistable.
Yeah. Fine. Yeah. Thank you.
And only, but actually it's potentially semistable everywhere because of this.
Thank you.
Okay, so this is the motivation. So now let's just go back to, okay. Yeah. So from now on, again, I've already said we'll take a greater than equal to 2, but one more assumption we need, that is n is greater than equal to 5. So this assumption is very important to construct the representation. It's crucially used. However, it's not that you need, it's not that, I mean, it's not true that you can construct representations only for modular forms of Hecke forms of level greater than equal to 5. That is not true. If you have a modular form of smaller level, then what you can do, you can view it inside a space of forms of a larger level. It will no longer remain a new form. It will be just an eigenform, but that is what you need actually. That will be eigenform, and for outside finite set of Hecke operators Tn's and not dividing capital N, and that much actually we need to construct the representation. So this is a important assumption for constructing the representation, but not really for the existence of representations. Okay, so we can safely make this assumption. Let me just briefly say describe these notations, and again I believe these things were discussed in one of the talk last week on modular curves. So a modular curve y1n is an open modular curve parameterizing elliptic curves E together with a point. So I am giving a slight, I don't know if the definitions I am giving and the one which was discussed earlier the same, but they're equivalent. So it's basically a curve which describes which parameterizes elliptic curves E together with a point of exact order n on E. And this is of course up to an isomorphism. So this, by that I mean it actually describes parameterized these tuples E comma P, where P is a point of order n on E. Okay, of course over algebraic closure, so over Q bar you can take. If you are looking at things over Q. So now, so this is what y1 and this is how y1 n is described, and In fact, this is, so of course usually one studies this, one defines it over C, but they can get a these exist in fact over Q also, or any Z bracket 1 by n algebra, and its compactification x1n then classifies pairs of so not just E and a point of order P, but with some additional properties. So this describes, so you have, so these are the x1n is a compactification of y1n. So all the points of y1n is here. So all the elliptic curves are this. They will be parameterizing these kind of elliptic curves plus something additional, and they are called what are called generalized elliptic curves. They are also sometimes called n-gons. So at cusps, the cusps will correspond to those additional curves. They are not actually elliptic curves, but something different. And usually the term for them is generalized elliptic curves. And yeah, and some additional properties about irreducible components of those curves. So here this is where this assumption n greater than equal to 5 is used. So once you have this, then there exists a curve, what is called universal elliptic curve E over y1n with a y1n valued point P of order n in every fiber. So now, so again, I'm not giving you how this is constructed, but I can just tell you that its points over C, for example, it looks like this. So its C valued points are these, and in fact, this is what is used. So to construct it, one first constructs is over C, and then I mean you first get a complex analytic manifold, and then you using correspondence between these analytic manifolds and varieties, you get a variety, and then in fact one can show that this is actually defined over again over Z mod n Z, again over is Z 1 by n, as I said, or over any Z bracket 1 by n algebra. So these points over C are crucially used in the construction of this E, and this universal elliptic curve E. And there is action of gamma 1n on this, and you go modulo that action. And as I said, this is what I have already said, it's defined over Z bracket 1 by n. So this is what I have remarked here. Now the space of, so I have described in a way the modular curves, but what about modular forms then? The modular forms can be interpreted as a space of sections of some holomorphic line bundles. Notation is omega kth tensor product on y1. So they are line bundles on this y1n. So what is the definition of this? This, what you do is that, so you have this universal elliptic curve E over y1n. So you can look at the zero section of this. This is a elliptic curve. So you can look at the zero section of this, and then with this map 0, you pull back here using O, this sheaf of relative differentials.
But
denoted by
this only gives even weight, no?
Sorry?
This only gives even weight modular forms.
So no, so if you look at gamma naught n,
But omega, dz to the 2k, dz to the k gives you modular forms of weight 2k.
Not really. So if you look at the map, it actually has all of them here. Why do you think that it just gives only even weight? Yeah, I'm not sure what is the problem here with. I'm looking at the modular curve y1n, not y0 n. and there is no condition on the event type either. Yeah. No, these are all the forms. Yeah. Okay, and inside that mk gamma, inside actually this would be 1. Inside this, you have the space of cusp forms, which are those given by those sections which vanishes on the cusps of gamma 1 n. So, and here is a another description of forms using what is called Cordera-Spencer's isomorphism. So you have this here sheaf of differentials here, omega 1 gamma n, and you tensor it by. So this isomorphism actually first one proves it for omega to the power 2 with omega 1 xn over c, and then tensors it with omega to the power k minus 2. Okay. Yeah. So, so using this, once we see that the space of cusp forms can be described using the global sections of this sheaf omega x1 n tensor omega to the power k minus 1. So this description is up to here. It's in fact over any z 1 by n algebra. But once I come to here, this one is over C. So looking at maybe the notation should have been bracket C here. Yeah. So now let me come to the construction of representation itself. So recall we had this universal elliptic curve E over y1n. And then we also have this embeddings of this. So we have x1n is a compactification of y1n. So we have this embedding here. It's an open immersion, and what one can do is you can look at the first higher direct image of. So you take the constant sheaf z on. So you have this map P here. You take the constant sheaf z on. You take the constant sheaf z on y1n and then take it via P star, take it to E, and then you take the first higher direct image of that. Let me just describe it on the stocks. That will be that gives an idea of what is this thing. So on stocks, that means at every fiber, this is nothing but this H. So this ES is for every S in y1n, ES is an elliptic curve. So this is nothing but this first homology group with constant sheaf z, which is actually free of rank 2, free rank 2 z modules for every S here in y1n, and then we can take the k minus 1 symmetric power of this sheaf. And this again, I think the Eclair-Similar isomorphism, I believe, was discussed a little bit earlier also. So there exists an isomorphism between this cohomology group once you tensor over C and the space of cusp forms, and here direct sum with what is, so I've written here sk gamma 1, or this should be, sorry, this would be capital N. So these are capital N, sk gamma 1 capital N. This is the space of this sk gamma 1 again capital N is the space of anti-holomorphic cusp forms. So with this, when I take the direction of these two spaces, this is isomorphic to the tensor product of C with this cohomology group. In particular, if I just tensor with R, then this is just isomorphic to the space of cusp forms. So this everything is happening over C, and the coefficients are here. They are actually three Z modules of rank 2 at every stop. But we want to get a elliptic representation. So yeah, how much time do I have? Do I have 2-3 minutes more, or
You can take Sudhanshu. That is fine.
okay, sorry. So now let
No,
us
it's
take.
fine.
Yeah, okay. So now let us take a QL vector space FKL, which is obtained by tensoring this FK with QL. Then we have an isomorphism. So it's coming from. So these are all. This X1 and C, they are manifolds, and we can have we have this isomorphism, basically tensoring inside and outside from algebraic topology. And then there is also a comparison between Tal cohomology group and these singular cohomology groups, and also comparison between the cohomology groups over different algebraically closed fields, basically C and Q bar. So if I combine all these isomorphisms, and there is a isomorphism from here to this Tal cohomology group with this FKL coefficients. Okay, so now all these are because Hecke correspondences are defined over Q itself, and so they all will be. Hecke, they all will be. So Galois action will be linear with respect to the action of Hecke algebra on all these cohomology groups. So we can take this ideal of Hecke algebra IF and go modulo. So we have this Hecke module and also a Galois module, because on Tal cohomology group Galois group acts. So we have this Hecke module and also Galois module, and actions commute with each other. So I can go modulo this ideal, and this will remain a Galois module. So this is what is called this VFI is actually the Galois representation associated to the modular forms. Of course, one need to can prove all the properties I described in the beginning. Let me just remark here that in the weight 2 case, it's okay. So there are two things I want to say. So first is one of the property I said that the representation was a 2-dimensional representation. Another thing was that another thing is the special case of weight k equal to 2. So in the for seeing why it's of dimension 2 or degree 2, let me just say that there are two things one need to use. One is the Peterson inner product itself. Using that, it can be shown that this SK gamma 1 and C is dual to itself. And the first thing is that, and another thing one need to use that this pairing, this HK. I have not written the full notation. I have not given you a full notation, but this is the Hecke algebra, and this is it's happening over Z actually, and this space of cusp form. So they are dual to each other with this pairing, this perfect pairing. So if you combine these two pairing, one sees that this space is nothing but it's actually a free rank 1 module over this Hecke algebra, and then Hecke isomorphism tells that this is a free rank 2 module, because there is because we had a space of cusp forms and then anti-holomorphic cusp forms. So it's rank 2 actually, free rank 2 Hecke module. In fact, this is also this is happening over C, but also true over Z itself. So, or maybe I should say here, sorry, it should be ZL rank 2. Yeah, rank 2, and hence this space representation space corresponding to associated to F and L is also a 2-dimensional representation. This thing is nothing but tensor product of this with algebra modulo IF. Now at weight 2, it's how do we see it's equal to it's the representation coming from the Jacobian of modular curves. It's coming from this isomorphism between the cohomology group of X1N and its Jacobian, whose dual is isomorphic to the Tate module of Jacobian twisted by QL. So these are the two things I wanted to state. Of course, one need to also show that, so we had a property that away from branch dividing the conduct level, the Frobenius was acting certain way, and that comes from Hector-Simra congruence relation, which also I think was discussed in one of the talk last week. Yeah, so I will just stop here.
Thank you, Sudhanshu. Thank you for the nice talk. Yeah, just thank you. Are there any questions or comments?
A lot of material.
Yeah, Professor.
I said a lot of material here.
Yeah. Correct. That's.
I think maybe
You, I think, suggested some references also, right?
yeah. So I wanted to write. So sorry, I didn't. I was to write it here.
But
but
there
I forgot.
actually in abstract I have.
Oh, I have given. Yeah, I have given it in this abstract. There are few more. You can. So maybe I'll send an email. So that would be good. Yeah. So yeah, there is a comment here, a question here that unramified representation factoring through the Galois group.
Yeah.
Maximal. So that is so yeah, QP. Yes, right. So if you have a Q representation, that's what it means.
Thanks. That's why I forgot to check this. Yeah, question. There are some questions posted in the comments.
Okay, semi-simpleness for L not P.
That is answered already. There is some confusion about simple, semi-simpleness and semi-stable. Here answered that.
No, so I basically forget all these complex. Just look at the finite group. So if you have a representation of let's say Z mod P, that's what I wanted to give this example, simple example. Z mod P Z, and if it's acting on a vector space of over a field of characteristic different from P, it will be semi-simple. But if it is characteristic is P, then it may not be semi-simple. And that one example I gave, that's what I meant. If I remember correctly, yeah.
Yes.
And one such example I gave. So I gave an example of not really related to ramified or unramified. It's something different. I think that already I have said. Yeah, so that's what that is also I said kind of briefly. I said that when I say upper triangular and on diagonal it is 1 1, that's what I meant. Okay, I just wanted to use that simple language of not wanted to use the term coming from Wittgenstein theory.
So when you mention when you say inertia group of the absolute Galois group,
yes.
Now Galois group is also kind of description of all finite dimensional field extensions of Q.
Yeah, finite field, yeah. Yes.
So in terms of that, what does the inertia group mean? In terms of the field?
Yeah, so inertia group is something, it's not, you cannot describe it purely looking at the just at the extension, but you have to look at what are called the residue fields. Okay, so it's something associated to a prime P. So I have a prime P, I want to describe the inertial subgroup there. So when I describe, and not just you have to look at the field, but inside that field, there is something called what is called ring of integers. So in that ring of integers, you look at the, so you look at the primes above that. So I have this extension, I have this K, and I have Q, and I have Z, and I have OK, it's called usually.
Yeah.
And there is a prime here. So above that, there could be several primes. So you look at one of the primes. So then here, so here is so if it is Galois, then it is G, and then inside that, so there is this whole description. Inside that, there is a decomposition subgroup, basically the group which fixes this P. And then once it fixes, then you can go through the residue field, and you can look at those things whose action is trivial on the residue field. So that's what it means, because basically it means that's what from there we get that GPU. From there only we get that GP mod the inertia subgroup is acting on, because the action of IP is trivial on the residue field. We get the action of GP mod IP is trivial on that that residue field, which is the extension of finite field, and that's why it's generated by one element, which we call provenience. So that's why whenever you have a representation on which IP acts trivially, it just means that the representation is nothing but a representation of Galois group of finite field. So in terms of
so in general, this little p will split in.
So it will,
some primes may occur with powers.
Yes, it can have several powers. It can have several primes. So
yeah. So corresponding to powers greater than or equal to 2, you get, there's something about that.
Those are the ramified primes.
Those are the ramified primes. Yeah.
Sorry, maybe I'm not sure about the question. What?
So it's a description of fields of finite extensions of Q. Now these fields are originally defined by certain polynomials. Polynomials are not unique.
Okay. So I understand. So you okay? So in that language you want to understand. So you have of course, because we are over Q, so you can it will be simple extension. So you will have a polynomial describing that extension, and using that polynomial you can describe what is called discriminant. Do you wanted to ask that? So then you have the primes dividing discriminant will correspond to the primes or inertia group is non-trivial, and the prime doesn't divide the discriminant, then you will have the inertia group will be trivial. That's what that's the description you wanted to ask, or yeah, I don't know. Yeah. Anyway, yeah. Okay.
Okay. Yeah. Thank you, Sudhanshu.
I have a question. So
yeah, sure.
Yeah. So given a prime L here, and you can find many primes in the coefficient field of the modular form F. So let's say we have two primes lambda 1 and lambda 2 above the prime L. So you have two Galois representation, right? Rho F lambda 1 and lambda 2.
Yeah, so actually that's what, in fact, that's what I alluded to. I said little bit. So Galois representation is actually inside this. So GQ to GL2 of QL tensor K, let's say KF is the number field corresponding to that Hecke form. So this thing is not even field. So in general, it's product of
F lambdas. Maybe we can write F lambdas.
Yes, the K of
lambda.
Lambda, then lambda dividing L.
Yeah.
Okay.
So my question is, So my question is,
yes.
So can you recover, if you know rho f lambda, the Galois representation, say rho f lambda 1, can you recover rho f lambda 2? How these representations, these distinct representations are associated, are related to each other?
So what do I say? Traces and determinants actually determine. So they are, how do I say that? Uniqueness should say that that's same, but so this APs are inside K itself, KF itself. So this is inside KF lambda 1 and lambda 2 both. Lambda 1 and lambda 2 both. And I mean, you wanted to know me that how do I, if I know, sorry, if I know the formulas on for 1 lambda 1, so that means I know the formula for all the traces and determinants. Okay,
yeah,
so
I mean,
basically, if I know
something like,
so that means, yeah, so trace and determinant and the fact that it's irreducible also tells you the what will the representation for other field also. So in that way you can say, but I don't know how do you, I mean, if you want me to ask that, can I give a formula for the formula is in terms of trace and determinant. Okay, so that will tell you what will be for other.
so basically what does it mean that this rho f lambda 1 and rho f lambda 2 are isomorphic, right? Because they have the same characteristic polynomial at each of the primes different from L and N.
Field coefficients are, it's like saying this, that you have a representation, suppose you have a finite group, you can have a representation inside. See, when you say two representations are isomorphic, that only makes sense if you have same field. So that representation can have image inside.
No, but we can consider this rho f lambda I in the composition of these two fields, right? This GL2 of k of lambda 1 times k of lambda 2, right? So we can view those representation in the compositor.
No, I don't know. They are completions. So I mean,
I mean, we can get a larger field which contains both the fields, right?
Yeah, you can get, but I don't know what will give.
Okay.
Of course,
and
yeah.
just one more thing. When you said that the representation rho FL is unique, so probably are you also using the fact using the fact multiplicity one theorem, that the eigenspace is one dimensional, or?
No, so I am just using the fact that it's the so you see traces and so Fourier coefficients multiplicity one theorem so that Fourier coefficient determines f. Okay, but it's the other direction. I am thinking that Fourier coefficients also determines, here it is determining lambda, it's determining Galois representation. So these are the two different statements. I'm not to say that representation is unique. I'm not using. Given a form, once you fix a form f, there is a unique Galois representation. That's where this for this consequence you don't need multiplicity one. But there are two different statements. One is that one is that f,
okay. Yeah. Thanks.
Okay, Sudhanshu. Yeah. Thanks a lot. So we can thank Sudhanshu again and close the session now.
Yeah.
Okay.
Thank you. Thank you, Sandip, for sharing this wonderful talk.
Yeah, it's a great pleasure. Yeah, welcome, Devendra.
Okay, Sudhanshu, maybe see you sometime again.
yeah, sure.
Ganesh,